Okay. Well, good morning and welcome everyone. Thanks for joining us for our now monthly webinar series. This webinar is titled Development of the NPDES Plus Analyte List for Produced Water Characterization, Treatment, and Reuse. My name is Zach Stoll, and I am the Assistant Director at the New Mexico Produced Water Research Consortium. And I will be your host and moderator for today's session. So very excited to have everyone here. Just a couple of housekeeping items before we get started. This session is being recorded and it's going to be posted on the website after the event. So if you miss something, you can go back easily and find it and then share it with your friends and your colleagues. We're also open to folks using or asking questions using the chat at any time. And then for recording purposes, we just please ask that guests turn off their video until the Q&A session. And if you experience any difficulties, technical difficulties, you can use the chat function and our support team, Rosa and Amanda, will be assisting you. So with that, I'm thrilled to introduce our speakers today. Joining us, we have Dr. Yanyan Zhang. She is an associate professor of civil engineering at New Mexico State University. Ryan Hall, who is the director of technical operations at NGL Energy Partners. Dan Mueller is he is a water resource engineering consultant, formerly at EDF. And then, of course, Dr. Pei Xu, who is our research director at the consortium and also the chief technology officer. So collectively, they bring a wealth of expertise spanning academia, industry, and applied research in water treatment, reuse, and resource recovery. And everyone's probably heard enough of me already. So with that, I'm going to turn it over to the speakers, and the floor is yours.
Thank you, Zach, for the very nice introduction. Good morning, everyone. Welcome to this webinar. And today, this group of speakers will talk about how the consortium has developed the NPDES Plus Analyte list, and we will also present some preliminary results on how we use this list to characterize the produced water and also evaluate the treatment efficiencies to ensure that the treated produced water would be safe for reuse. So I would like to give a very brief introduction about the New Mexico's energy landscape. New Mexico is the second largest oil producer in the United States and is among the top natural gas producing state. And a large amount of produced water actually is generated in New Mexico, along with oil and gas exploration. It's about 1.9 billion barrels per day, or over 5 million barrels, 1.9 billion barrels per year, and over 5 million barrels per day of the water is generated. About 98% of the produced water is generated in the Permian Basin, and then another 2% is in San Juan Basin. The produced water contains the formation water, injection water, and the chemical additives. For New Mexico, because we are in a very dry area, and it is important that we can treat this water and to augment the fresh water supplies. And at the same time, produce water treatment and reuse could reduce environmental impacts and mitigate the induced seismicity. So the consortium was established under the 2019 Produced Water Act. It was created by the New Mexico Environment Department and the New Mexico State University. The mission of the consortium is to address the key scientific and technical challenges in produced water treatment and reuse, and provide the information, the data to inform the policies and regulations based on the science and the technologies. And in addition, the consortium is leading an integrated research, education, and outreach effort. The consortium has formed an extensive public and private partnership and involves the federal and state agencies, industry, NGOs, environmental groups, and academia. So for the consortium, our goal is to transform produced water into a reusable water through the science and innovation. So we have been working with consortium members, the technology developers, to evaluate the produced water treatment technologies through the pre-treatment and the desalination technologies using the membrane-based and the thermal-based treatment processes. And we also evaluated the different types of treatment post-treatment processes to make sure that the treated produced water could be used for different fit for purpose applications. In order to make sure these treated produced waters could fit the beneficial use applications, we use a very comprehensive evaluation framework. It includes the targeted analysis, non-targeted chemical analysis, and the whole effluent toxicity, including also the in vivo and the in vitro assessment. And we are also performing fate and transport studies, including the model simulations. And then we have different types of risk assessment tools to evaluate the risks and toxicology of the treated produced water for aquatic life, human health, the soil health, and for plant growth. So when the consortium was created, Mr. Mike Hightower, the former director of the consortium, and along the consortium members have created 6 working groups. It includes the water quality and quantity, risk, toxicology, data management, infrastructure, treatment, education, outreach, and the multi-state coordinating working groups. And the NPDES Plus test today we are talking about were actually developed by the first 2 working groups, water quality, quantity, and risk and toxicology. And later with the completion of the NPDES Plus list, and then these 2 working groups are later merged into one risk and toxicology working group. So in the first 3 years, we had the kickoff meeting in the early 2020, right before the COVID. And then in the first 3 years, these working groups have been working very diligently to develop this NPDES Plus list. And we have bi-weekly meetings, and we had over 20 members participated in developing this list. It includes regulatory agencies, federal and state, academia, industry, and NGOs. So today, Dan, Ryan, Yanyan, and I will work as representatives of this NPDES task force to present how we have developed this list. So before we go to the list, I want to talk about what is NPDES. I think everybody is familiar with it. This is the National Pollutant Discharge Elimination System, and this is the permitting system established by the Clean Water Act that regulates the discharge of pollutants into the U.S. waters. And the list, we call it NPDES Plus list, actually extends beyond the surface water discharge requirements. And it includes the analytes, parameters relevant to beneficial use applications, such as industrial uses, agricultural irrigation, land applications for the treated water. So the objective of the NPDES Plus Task Committee are to identify the analytes and then to provide the interim treatment guidance for bench and pilot testing projects so we can characterize the produced water and the treated produced water quality with the goal to protect the environment and public health. And another goal is with this list, it will help us to reduce the time and economic burden to analyze the water quality and to monitor the water quality. So to begin with, we conducted extensive literature review to document all the NPDES Plus analytes or the standards or water quality requirements for discharge and beneficial use in different states. And the eventually goal is to fill the scientific and technical knowledge gaps on the NPDES plus elements that are necessary to establish regulations and policies for the treatment and the reuse of the produced water. So after that, I'm going to hand it to Dan.
Okay, thanks, Pei. And I was scrambling there for a minute. I've lost the internet. Who knows why? It shouldn't be that unstable around here. But so if I go, silent again, please take up on the slides. I just have a few. So, but thanks. And let me, start off and just talking a little bit about, well, what is produced water? Now, what is this fluid that we're now looking at in detail for potential beneficial reuse? And I don't know, most of you on the call probably know this, but just to kind of set the foundation here, basically produced water, it's everything that is exiting from the well for the life of the well, oil and gas well. It's more than just the injected fracturing chemicals that are coming back with flow back. It's more than the constituents that are trapped with the oil and gas formation, but it's a combination of all this over the life of the well. It's lots of stuff in it. It's more than just total dissolved solids. That's a lot of what gets focused on. It's typically higher than other waste streams. But it also is a very variable fluid. It varies by location. It varies by time. So you have a fluid that is changing in constituents over these different parameters, which makes it a challenge. Next slide, Peg. So like I say, it's more than just the formation water. It's more than just total dissolved solids. There's other inorganics and organics, potentially radionuclides that are in this water. Certainly fracturing chemicals. Some of those do return to the surface over the life of the well, but there's more than just fracturing chemicals that are used, that are injected through the course of oil and gas production. Fracturing chemicals are there for the completion of the well initially, but ongoing maintenance chemicals for the life of the well are also injected. Some of those will also be then returned to the surface along with the water and the oil and the gas that returns to the surface. There's also the fact that these chemicals are present, some chemicals being injected in a situation in the oil and gas well that's high heat and high pressure. Therefore, there are chemical reactions that will be occurring. So there's been some research into, well, how about these daughter products or these transformational products that can actually be generated through the mixture of these chemicals and also exit the well, which means that weren't constituents that were initially present in the oil and gas formation, nor constituents that were injected, but some sort of combination. Again, complicated, something to look at. Next, please. So, and Pei kind of walked through this really quick, but right before, but is the situation and the question was put forth to a group. They're like, well, how do we develop a list? Well, let's start with kind of looking at various information sources that we can just start to pull on. One is the regulatory program and guidance of permits. Now, that's this information source, but this is a relatively new industrial wastewater stream. There are some permits that have been issued in other parts of the country, different situations than we have maybe in the Permian, but certainly an information source to look at. But again, these were not all the situations that line up with what we have in the Permian, but certainly something to look at as far as some previous NPDES permits that had been issued. There was a focus on approved analytical methods, and approved analytical methods are just methods that have been basically developed and used for regulatory purposes and can be used for regulatory purposes. And what it means is that there is basically, there is a method, a defined method for sample prep, method of analysis, calibration standards. In essence, approved analytical methods are methods that a commercial lab will typically be able to run. And that certainly kind of gets back to, well, we got all this, samples coming up. We want to be able to rely on, where we can, commercial labs to do as much of this analysis as we can to give us some data points and such, but also then build upon that. We also build upon some similar efforts. A number of years ago, there was a group up in the Marcellus. It was initially called Center for Sustainable Shale Development. That was looking at some of the an NPDES treatment operations that had NPDES permits that were treating oil and gas produced water. And so there was a collaborative effort at that time to look at beyond just what that permit had required those facilities to look at. And so there was some work done back then. There was certainly look at what has been done by other groups before and then build upon that. Yeah, look at peer-reviewed literature. Got some great researchers, both in academia and in industry, looking at this. So build upon that, and of course that feeds into just the expertise of the consortium members. We've got a collaborative effort of a lot of folks looking and doing that, and working together on that. So this list of analytes, we certainly have to cast a wide net to try to capture as much as we can to build this foundational information about, well, what is in this fluid, what is likely to survive treatment, and then be also looked at and as we look at pilot facilities and evaluating the research in that arena. So it kind of breaks down to these different constituents that are pertinent to look at. Conventional water quality straight off the bat. And what is that? Well, those are things like temperature, dissolved oxygen, nutrients, dissolved solids, and such as that. Inorganics, certainly look at those. Now, there's a list of inorganics that helps us, right? We have a list of known inorganics to take a look at. That helps to put that list together. But then we go to organics. Well, now that's more of a challenge. Uh, for number one is that there's, we're in and we live in an organic world. There is a huge population of organic constituents that are in and around us. Some of these organics, we have approved analytical methods to look at, number that we don't. Some of these organics, we certainly have toxicity data that we can rely on. Many of these we don't. So that casts a very wide net as far as what do we look at? How do we address these organics that are potentially present? Then we have other specific target analysis, radionuclides. PFAS has been kind of it's certainly an emerging topic these last number of years. There's also, other emerging constituents that are always that need to kind of take a look at. And the NPDES program does kind of factor into that, looking at emerging constituents. So we need to be certainly familiar with that, or at least aware of that as we're kind of looking at, well, what is this list? What would this list be comprised of? So that gets to the unknowns. Now, this gets to items of where, okay, there's constituents there that we don't have approved analytical methods for. We may have research methods, or what we call, untargeted analysis, trying to parse down with, well, what we think could be there. And of that, then look at what the toxicity may or may not. But need to look at what the potential unknowns that we don't have general and a commercial lab would be able to look at. Although a commercial analytical lab can look at what's called tentatively identified compounds. We added that, and there'll be, I'm sure, some more conversations about that through this presentation. That, in essence, is taking a look particularly at organics, where because of the results that come back from an organics and running and going through a library search, a lab can say, well, because of the peaks and such that are being exhibited, this could be this constituent that matches that. Tentatively identified compounds is a very useful tool. It is useful in identifying what potentially could be there. It doesn't give you any information about its concentration, but it tells you there's something that could be there that you need to look closer at. And then we have the toxicity. And whole effluent toxicity test is a very established, well-established test for aquatic. But there's also some other toxicity, and there'll be conversations about that as well to look at. So, list is long, and as Pei mentioned, and you do cast a wide net. There is a goal to kind of start to narrow that list down. Once you get enough information to be able to narrow that list down, it does require a lot of data gathering, a lot of analysis of the data. How much is enough? Well, that's a really good question, but it is basically you got to start somewhere, collect as much as possible, and use that then to start working at, well, what should we be more focused on or not, and sort of a prioritizing what to look at. So I'll pass it on. Thank you.
Okay, so what we're looking at here is a matrix of kind of our approach. Like Dan said, we want to cast a wide net and we want to be using, to the extent possible, accepted laboratory methods and procedures. One of the challenges that we were facing with this, still facing with this, is the treated effluent that would be analyzed by certain methods congruent with NPDES methods. So standard methods, 600 series methods for the organics. They're very prescriptive. The problem is those methods aren't acceptable for the matrix of produced water, specifically the very high TDS. So when we were looking at initially characterizing this, we had to um, shift gears a little bit and look towards more of the SW846 methods, and we'll talk about that a little bit later on. But what this slide shows is initially we're breaking everything up into major components. So basic water quality, the inorganics, the organics, the radionuclides, and then the biological processes. So that's what you're looking at going across the top. Going down is within each one of those, one of the important things is the sample collection. It needs to be in the proper bottleware, glassware. Oftentimes, for specific methods, they will have preservatives to eliminate certain things that might be in the water. So, for example, for your organics, it's usually HCl preserved to kill any microbials in there that could degrade your present organics in there between the time of sampling and the time of analysis. Also, the bottleware itself, if you're doing anything organic, you don't want to use plastic bottles because you're going to see phthalates from the plastic bottles ending up in the analysis. What we're looking at is to a level of sensitivity that can pick up these very, very small levels of contaminants, oftentimes that are present in the pre-cleaned bottleware anyhow. So that's what you're seeing across the sampling and preservation. Zero headspace to keep any of the dissolved gases, the volatiles in the water phase until it is time for analysis. Um, Poly bottles for your inorganics. So anytime that there's a sampling event, you might get 5 coolers with 65 different bottles to capture enough water in this specific type of bottleware that the lab can then do a legally defensible analysis on. So once you have the sample and once it gets to the lab, there's various different ways that they're going to pre-treat this. So for example, your basic water quality, you're looking at, what could be filtered. So it's going to be the water is going to be passed through a 0.45 micron filter, and then the residue on that filter is going to be analyzed. For your inorganics, oftentimes you're doing an acid digestion to make sure that any of the non-dissolved species are now acidized and dissolved, and they could be visible to the instrument. And then for your organics, you're doing either liquid-liquid extractions, solvent extractions, um, purge and trap, where you're actually volatilizing off the organics and then putting that onto a cold trap and then releasing that into the analyzer, or solid phase micro extraction. So various different techniques targeted to the specific analytes that we're trying to see. So if you think about, for example, the inorganics in this produced water particularly, we know that there's an awful lot of sodium and chlorine. So if we're looking for maybe sulfate, that peak on ion chromatography can oftentimes be overshadowed by the sodium peak. So it's important to have methods that can differentiate between those two. And specifically with your ICP-MS, it's very difficult. If we're just doing ICP, some of the wavelengths for some of the other elements might be overridden by the abundance of the sodium that's there. So what we chose multiple different methods so we can look at things through different ways to minimize the amount of matrix interference. Next slide, please. These images are from a an RFI that we did, I want to say in 2020, where we were soliciting laboratory services. And what we wanted to, and then these ultimately made it into one of our publications, but what we were looking at two different things. Tiered testing. So if you look at conventional NPDES permits for industrial wastewater discharge, their monitoring is usually broken into tiers where they have routine, continuous monitoring for indicator species. Then you have maybe daily monitoring for a smaller, I'm sorry, for, yeah, a smaller component of that, but they're still surrogate compounds. And then maybe on a weekly basis, you have a little bit bigger. And then maybe on a once per year basis, you have maybe all of the analytes. So based off of that model, we wanted to build this, and as Dan mentioned, there were a few discharge produced water discharges already before we did this, but in all of those things were different. So, for example, NGL had a facility in Wyoming. The TDS was much lower. So we could use conventional treatment technology, and the water that we were discharging, so the amount of material that we were discharging would be able to be, for lack of better terms, diluted by the relatively large volume that we were discharging into. That is absolutely not the case in the Permian Basin in both. The TDS is very high, so most conventional um, treatment processes wouldn't be able to, off-the-shelf processes wouldn't be able to give a treated water that would meet what we were looking for. And more importantly, the receiving waters, or in many of these cases, dry riverbeds, there is no dilution. So whatever we're discharging is going to be there in the environment. So we had to be very thoughtful in how we approach this. And that's why in this tier testing, we're looking at continuous things. We're looking at inline sensors. And for example, I'll use TDS. If our TDS is, let's say, 100 on a continual basis, and we know that nothing is changing on the influent side and nothing is changing in the treatment side, I have pretty good confidence in that number. And based off of that TDS and past analytical, more detailed analytical, I have a good feeling of what individual constituents are contributing to that TDS number. Okay, so tier one, your TDS is pretty flatline, and I have a good idea on what that is. So under tier two testing, that TDS, we would then speciate that through ICP and ICP-MS and ion chromatography to identify all of the inorganic things that are there that are contributing to TDS. So on a tier two level, we're doing more of the conventional laboratory analytical that gives us um, the the what the element is, sodium, and what the amount of it is. So under tier three, this is where things start getting a little bit more interesting from my standpoint. We're looking now at maybe what's in our waste stream. So your TCLP, what's leachable in that waste stream. So in these processes, we're going to have to do pretreatment that's going to generate sludges. So, with respect to the TDS, what's the amount of barium that would end up in our pretreatment sludge? And from a wet testing standpoint, we are looking at the toxicity in acute and chronic applications. And then tier four is really very specialized, where we could be looking at through scanning electron microscopy, specific morphology, particle size, elemental mapping of what these things look like, X-ray diffraction, where it's not only let's say specific to barium, it's not only the element, it's the actual species. Is it barite? Is it a wear debris from something in our process? So this is an example of just looking at TDS, how we can go from tier one, very general, all the way down to highly specialized. And then the graph on the left shows cost on the vertical and time on the horizontal, where these things kind of fall. So your field analysis, that's your Hawk spectrophotometer. It's very cheap. It's very quick. It's getting you it's getting you data that's not necessarily legally defensible, but I get it now. So I can see if something is in spec or out of spec. Oftentimes, that same analysis from a third-party laboratory, it might take a week or more. So there's a need to be able to get maybe 50% quality data now versus 100% quality data 2 weeks from now. We're going to be doing both, but it's important to be able to get data now. So as you go up kind of the ladder here, filter analysis is the next. So this is what most people use in the field right now. It's you're filtering the water through a millipore filter, and then the laboratory does sequential extractions. So it gives you analysis on the oil, the total solids, the total dissolved solids, the oil soluble, the acid soluble, and then the insoluble. So based off of that, we know that roughly um, the majority of the components fall into any of those buckets, and based off of that, it tells us what's going on. And this would really be on the raw side, not the treated side. Then you have your conventional laboratory testing, and most labs now can do things in 5 days. So your time, it's kind of middle of the axis, and then your cost. The majority of the analytes that we're going to be looking at, we can get through a handful of these methods, GC mass spec, ICP, ICP-MS. That's going to give you a lot of the things that we're looking at, and you're looking at maybe $500. So it's not super expensive, and you can get it pretty quickly. Now, as we go up, you have your lab testing, your unconventional. So this is more of what Dan was talking about, and I think others will talk about later. These are um, more bespoke methods, maybe still in the development phase. They're more expensive because the equipment is much more expensive. Your toxicity testing is more expensive because you're sending large amounts of water. There's not a lot of toxicity labs in the United States, so you're shipping them across the country, and then they're exposing organisms to them, and then they're doing the data on the back end from that. So it takes a lot of time, and it takes more money, mainly on the logistics. On the time standpoint out here, your radiological testing, the prime reason for this is we have to allow in-growth time for radium-226, and that's a minimum of 21 days. So from the time that you sample, you send it to the laboratory, and oh, by the way, there's only like 2 or 3 laboratories in the country that do this testing. So oftentimes there's a long waiting list. Your samples are going to be waiting in line before they get to be analyzed. And once they're prepped, then there is a 21-day in-growth period. And then after that 21 days, then the analysis happens. So the same could be said for the PFAS testing, dioxin testing. Um, there's just a very long wait time from the labs because of just lack of analytical capacity. So you can get all of this stuff back within 5 days, but you're not going to get the radiological testing back for, upwards of a month. And then way out here on the end of time and cost is the forensic testing. Next slide, please. Okay, so that's the background. And here's a couple of slides with how we came up with the NPDES Plus list and why. So there was a paper published by Chloe Danforth and others in 2019 where she it's we refer to it now as the infamous Chloe Danforth paper, and she jokes that it was the bane of her existence because now everybody points to that as the list. And what I've said to her is, look, at the time there was no other list, and engineers and scientists, we need a list and limits to treat to. And because there wasn't anything better than this, we use this as the original high water mark. And I took this list and I worked with Eurofins to establish a program, an analytical program that would capture as many of these constituents as possible. I think at the time there was, roughly 300 plus or minus, plus, not minus, target analytes that we were able to build this analytical program around. And we told the lab to look for tentatively identified compounds, TICs, for both the volatile organics, the non-volatile organics, and so GC mass spec and LC mass spec. So that was kind of the start to create this program. The first thing that we did was work with a laboratory to build an analytical program and identify the methods and then the analyte lists and build some infrastructure around that where we could use the same thing over and over and over again. Next slide, please. Once we built that list, we worked with Tetra Tech to begin collecting samples on a biweekly basis from one of our facilities, our Striker 1 facility at the back end of treatment. So what that means is the water comes in by pipeline and we get a little bit of trucked water there, but it goes through sand tank settling. So basically primary gravity settling, all of your settlable solids come out. Our gun barrels, so our oil water separation. Then we have some additional water tanks out the back where you have equalization. So equalization occurs, and then it passes through a filter pod. And I think at the time we were using 200 micron, 200 mesh filter socks. And then at the end, that was the water that we selected to analyze. The reason we selected it there is if there was any subsequent treatment, it would always be downstream of that process. So, keeping in mind this was 2020, there weren't any field pilots at that time in the Permian Basin. Since then, we've used that model. The field pilots we've done, and we're doing one right now at Striker 1, is below that process that I just described. So we took samples from there, and we took samples from the Pecos River, which is just nearby. We're right above Malaga Bend, and we wanted to analyze both to establish baseline conditions in the surface water before any discharge has been in there, and then also establish baseline for what our raw produced water was, and also get a feel for variability. And that went on for a period of 4 months. It went through that analyte list that I described in the last slide, and then we ended up publishing this, and that data has been out there, and that it served as a good kind of baseline for both the Pecos River and raw produced water in the southeastern New Mexico. And as Dan said, spoiler alert, there's a lot of organics in the surface water environment. So there was things that we were finding in the Pecos River that really isn't in produced water. Next slide, please. So that was kind of my best stab at what we thought the list should be. And from there, we did this as NGL for our own uses, and then we shared that with the consortium. And then from there, the working groups wanted to build some additional guardrails around that. And we used kind of the Danforth list through Eurofins, kind of the project infrastructure that we built with Eurofins as the starting point. And then we went from there. So at the time, one of the other members in the risk and tox group, Josh Butler from Exxon, He's since moved on to another role within the company, but he was doing some really good work with new fields, and their list was a little bit more comprehensive than ours. And so we crosswalked that list with the NMAC. So all of the constituents that are enumerated in the New Mexico Administrative Code. So in some instances, there were ones that were on the new fields list or the Danforth list that weren't on NMAC. We kept those in there. And then there was a few instances where they were in the NMAC that weren't in either the Danforth list and the new fields list. And typically those were things that really have nothing to do with produced water, such as organophosphorus pesticides or maybe tritium, things that might be specific to New Mexico that aren't really specific um, to produce water, but we kind of call those out on the lists. And we debated, well, do we really need to include, for example, asbestos is one of the things that is in the NPDES list, because in some areas geologically you could have asbestiform material in there. And I think that's one of the things in the EPA drinking water list. Very, very, very low likelihood of that being in raw produced water, let alone treated produced water. But it made the list. So what we wanted to do is create as comprehensive of a list as possible, and then use established third-party laboratories to be able to provide legally defensible data. Um, as Dan said, ticks, your tentatively identified compounds. What's interesting about that is, we have 350, I don't pay knows the exact number of target analytes, but in addition to those target analytes, a tentatively identified compound list uses the mass spectra library for the instrument. So there's different lists for your GC mass spec for the volatiles versus the GC mass spec for the semi-volatiles versus the LC mass spec for those non-volatiles. And any mass spectral fragment that is seen by that, the library will give you a recommendation of what that mass spectra would be. So for example, benzene. Now that is a targeted analyte, but I'm using that as an example. The mass spectra is consistent with what benzene mass spectra would be, and it would give you a confidence number for that, and then um, an estimated concentration. Now, over time, what's interesting is each of those libraries are hundreds of thousands of constituents. So we're getting visibility we're getting legally defensible data on about 350, and then um, we're getting non-target estimated detections through the ticks on a vast array of others. What's interesting is if we're seeing the same tick in the water over and over and over again, what we can do is now develop the method, whether it be 8260, 8270, or one of the LCMS methods, to take that from a tentatively identified compound to a target compound. Um, Most of the target compounds now were once tentatively identified until that method was developed. And how they do that is through getting standards for that compound and building a calibration curve, and then and a second source standard. So, we're sure of what we're seeing there. And then we can move that from an estimated detection over to a target compound. So over time, as we're seeing these things, the methods can adapt to include maybe some of the daughter compounds or the breakdown compounds or the unknowns. As we see them over and over again, we can bring them into the fold into a legally defensible um, fully enumerated compound. Next slide.
Okay. Thank you, Ryan and Dan, for the excellent discussions and the history of how the NPDES Plus list was developed. And what Dan mentioned, Ryan mentioned about the sampling protocol and the NPDES Plus list are already in the consortium website. You can download those. And also the papers that we presented today are also in the consortium website you can reference to. So here is an example how we use the NPDES Plus analytical list to do sampling and also water quality analysis. This example is for the thermal distillation. NMSU team went to the field and then collected the raw produced water, thermal distillate, concentrate, and post-treated produced water. And then we sent the samples to Eurofins for analysis. As Ryan mentioned that we did the RFI in 2020. We sent the request for information about the analytical methods to different analytical labs, certified labs especially. And then Eurofins was selected because they can do all the analysis in the NPDES Plus list by the same the Eurofins labs. So here is all the tier 1 approaches, and then this is the tier 2 approaches with all the metals, and then this include the anions and radionuclides. Then for the organics, it has a very long list because this is a very wide nest. We try to capture all the oil and grease, semi-volatile organic compounds and volatile organic compounds, pesticide, herbicides, PCBs, PHS, and TOX, and all the PFAS compounds. So we try to make the list very broad, and also the tentatively identified compounds for the VOCs and semi-VOCs. And again, another list that is in the New Mexico Administration Code for the surface water, groundwater regulated, and then also include the rare earth elements. So the tier 3 involves the whole effluent toxicity test that we send only the post-treated water because, we want the water has remove ammonia and other constituents. We know that they are toxic, and we may need to re-add the minerals back to the post-treated water. So the minerals will not another reason for the failure of the treated produced water for whole effluent toxicity test. In addition to the analysis in the certified lab, NMSU also conduct the non-target analysis using the high-resolution LC-MS at the Chemical Analysis Instrumentation Lab. And Dr. Yanyan Zhang will talk about the toxicity study for the wet human cell line mice toxicity study. And so we also have the College of Agriculture, Dr. Manoj Shukla also did the irrigation experiments to evaluate the treated produced water for plants and soil. And we also collaborate with Texas Pacific Water Resources to evaluate their greenhouse experiment. There are also ongoing research at NMSU on the irrigation experiments. And we also conducting the fate and transport study and model simulation of applying treated produced water to the soil. So I would like to give some examples of how we use NPDES Plus list for the produced water characterization, and the work is still ongoing. And this is the results of the targeted analysis. So we collect 10 sets of samples for including, let's see, 4 thermal treatment technologies at a different time, and then also include some research results from Colorado School of Mines, and then the other membrane-based technologies. It's marked as T for thermal and M as membrane-based technologies. You can see that we analyzed in total over 600 compounds, and across all these 10 sets of samples, about 290 compounds were detected at least once in these compounds. The color codes showed the categories of the analytes, including, for example, the wet test, organics, petroleum hydrocarbons, and total organic halides, and pesticides, herbicides, radionuclides, and dioxins, PFAS compounds. So this is a very comprehensive analytical list. And we also did non-target analysis at NMSU, including the solid phase extraction and the mass spectroscopy using the MZ-3 for the pig identification and predicting the molecular formula structures. And then we identified the suspended compounds. And then after that, we use the US EPA tool, cheminformatics, to identify the toxicity of these tentatively identified compounds through the NTA analysis. This is an example of the research results using the targeted analysis and non-targeted analysis to characterize the produced water treated by the membrane distillation. So the membrane distillation involves the vacuum technology, and also we coated the ceramic membranes with the photo catalyst to improve the treatment efficiency. So we call it VMD and PMD treatment processes. And the non-target analysis results has been published in the Journal of Hazardous Materials and in collaboration with US EPA. And then the vacuum membrane distillation paper was also published. And you can reference to these papers for the details. So for targeted analysis, we found the membrane distillation can remove dissolved organic carbon between 77 to 90%, and the salt rejection and ammonia rejection achieved over 99%. But we also detected the gasoline range, diesel range, and extended diesel range of organics with concentrations less than 1 milligram per liter in all the samples, and only 6 VOCs compounds were detected in the feed water, and in the thermal distillate, all the compounds, including the methylene chloride, benzene toluene, and the total xylene, were detected with concentrations less than 0.5 microgram per liter. So this graph shows the non-target analysis results. In total, we identified 790 features, and then 75 compounds were shortlisted as the tentatively identified compounds across all the samples. And then you can see that the feed water has identified about 65 compounds, and then in the thermal distillation, the identified compounds were reduced to about 20 to 30 number of compounds. And the reduction of the number of identified compounds is consistent with the reduction of the TOC. From the feed water, the TOC is about 45 milligram per liter, and in the thermal distillate, it's about 5 milligram per liter. So after we identify these compounds, we use the cheminformatics to predict the toxicity of these compounds. And then in this graph, you see the red color shows highly toxic, and then the green color shows low toxicity. But it should be noted that these toxicity predictions are based on the concentrated organic fractions, and the actual concentrations of those identified compounds through the NTA actually are unknown. We don't know their concentration because non-target analysis can only predict the presence of those compounds. We don't know their concentration. If we want to know the concentration, and for those very toxic compounds, we need to convert it into the non-target analysis. So the actual concentration could be very low in the treated produced water, may have negligible toxicity. So the next step of work of the toxicity study is very important, and Dr. Zhang will present those.
And get started. Can I share the screen?
Yes, I will stop sharing.
Right. Good morning, everyone. First, I'm going to talk briefly about why we are selecting certain type of wet assays, and then I'm going to give you a summary about the wet test result we have for several pilot scale treatment facility. So I mean we select those type of wet assay based on the NPDES requirement. So for the acute testing, we need at least 2 species, normally fish and the invertebrate. And for the chronic test, we need 3 tropical level of the organism, like fish, invertebrate, plant, or algae, to meet the requirement of a taxonomic diversity. So for municipal wastewater discharge permit. So those 3 are the most commonly used organism for the permitting purpose. So the fish so it has a common name of fat minnow. So it can be used for both acute and chronic assay. So a chronic, the survival, mortality, chronic means a survival and growth after 7 days. So for the invertebrate, we are using one type of water flea, Ceratophrenia, dubin. So it can be used for both acute and chronic as well, acute 48-hour survival rate, and chronic is a 6-day or 7-day survival, and the reproduction of the next generation we call nemonate. And we also use another a freshwater algae species. So to do 96-hour chronic test to see the growth inhibition. So I know some people also using another type of water flea, such as Daphnia magna, Daphnia pulex. The only problem for those things is they can only use for the acute acid, not chronic acid. And compared with those type of water fleas, are definitely are more sensitive to the salinity of water and for many compounds in the water. So for the treated produced water, we have been used the following organism for the whole effluent toxicity assays. So those has 4 tropical levels that cover across the whole food chain. So we have the bacteria as decomposer. So we have the algae as producer. So we have the Ceratophrenia as the first level consumer. So we have the fathead minnow as the second level consumer. So we also add another zebrafish embryo test just to verify the human health risk, because we share 70% gene with the zebrafish. So that's why zebrafish is ideal model for the toxicity assays. So we get different type of endpoint. So for example, we have the we determine no observed effect concentration. We determine the lowest observed effect concentration. We determine what is the concentration cause 25% inhibition or 50% of mortality. So here is the summary for a thermal process. We had 3 pilot study so far. So as you can see, for the raw produced water, they are very toxic. So you can see the 100% of water, so causing 100% of mortality. And also, so the LC25 or LC50 is very low, very small percentage. That means they are very toxic. At that percentage, already cause 25% of inhibition or 50% of the mortality. And the LOEC and NOEC concentration is very low. I mean, by the way, we are using the standard dilution, 6.25%, 12.5%, 25%, 50%, and 100%. So after thermal distillation process, so the toxicity is reduced, although they are still causing almost 100% of inhibition or mortality with 100% of thermal distillate. However, the IC25 or SC50 significant increase. That means the reduction of the toxicity. So as we know, thermal distillate still have the residual organic compounds and about 20 to 40 milligram per liter of ammonia. So those compounds are causing the toxicity. So that's why post-treatment were performed by using the GAC zeolite or other process to remove those residual organics and ammonias. So after post-treatment, as you can see, all the NOEC, it means at 100% level, we didn't really see the some impact, and LC25, LC IC25, LC50 is more than 100%, and the impact at 100%, that's based on the EPA test of significant toxicity method. So normally when they less than 10%, we said that's the the effluent is non-toxic. So and also we if it's less than 20% for the acute assay, less than 25% for the chronic assay. So we also feel there is not much risk. So for the discharged water. I mean another thermal process number 2 give us the same result. So for the third thermal distillation process, so we did find some toxicity for the 100% of treated water. So as you can see, I mean only the algae test. So there is no impact, and but all the Cerodaphnia or Daphnia Pulax and Phemino, so we have some impact. So the main problem for this thermal process is we found high concentration of methanol in the final effluent, although they already use the post-treatment to remove the organic compound, to remove the ammonia. However, we still see 20 milligrams per liter of methanol in the final effluent. So that's why 50% produced water is okay. So the NOEC most case is 50%, so no observed effect. However, as long as we can increase the concentration to 100%, we start seeing the problem. So I mean, as you can see, those wet assays are very sensitive. So those are the slides. Actually, this is a result from the membrane process. Sorry about the title. And we did see the same result. So actually, after the RO, reverse osmosis treatment, and sometimes there is another final step to further polish the water. So we didn't really see any effect at 100% of treated produced water level. So everything is 100 or higher, 100%, and all the effect at 100% is less than almost 10% or at least 20% in all the cases. So those are the published paper. So left 2 paper, that's about the toxicity result for the thermal process. On the right one, we have some toxicity assessment result by using the human cell lines because we want in addition to those aquatic organisms, we do want to evaluate the risk of those treated produced water on human health. So that's why we are using 4 types of human cell line right now, including the breast cancer, kidney cell, liver cell, lung cell to cover the major organs in human. So we use exposure time of 24 hours. So we did a test with different endpoints. For example, we use 3 types of the assays to evaluate cell availability. So we test whether there is enhanced or reduced apoptosis. That means the programmed cell death. And we see whether there is increased oxidative stress. So whether there is an activation of the aryl hydrocarbon receptor. So that's kind of a xeno biotic sensor. So that means as long as we have some compound, aromatic compound especially, so these transcriptome factors will be activated, so they may generate some toxic intermediate and causing the even causing the cancer. So I'm sorry. And we also test whether there is a estrogenic activity caused by the treated produced water. So the human cell line is in vitro assays. So in vitro assay has some limitation. So they cannot represent the complex biological system. So that's why we also use the like mice as the like toxicity model. So while using some like outbred like mice strain, so outbred mice strain, that means like they have like variety of genetic background. So just like a human population. So compared with those like inbred, that means the pure strain. So it can like really represent the toxicity for like the people with the like diverse genetic background. So we did both acute acid and like with a 28-day exposure. So we feed like mice treated produced water, and we also did the subchronic acid like for 100 days exposure. So we test whether like they have the abnormal weight gain, whether there is abnormal blood like hematology and blood biochemistry indicators. We also like take the liver and see whether like there is liver cell morphology change. And we also like test the RNA expression in the liver to see there is like any abnormal or like change the gene expression pathway. So, and for the human cell line analysis, we found that so actually, like the human cell lines are not really sensitive to the residual organics and ammonias in the thermal distillate. Although they are sensitive for the raw produced water, still like about like 6.25% raw produced water is already causing the impact. But for the thermal distillate, as you can see, so there is like no impact on the human cell lines for the cell availability. So for all the assays, so we didn't find any impact. For the post-treated water, of course, no impact as well. So, but we did find activation of arohydrocarbon receptors. So that means those human cell lines are sensing the residual aromatic compounds in the thermal distillate. So that means we still need to do the like post-treatment for the thermal distillate. So the good thing is we didn't find any like estrogenic activity in all the like distillate or like or after post-treated water. So membrane process tell us the same story. So no like impact on the cell viability for all the like human cell lines. Like there is no activation of the arohydrocarbon receptor. That means so RO permit doesn't really have any like aromatic residues, and there is no estrogenic activity in all the RO permit. So for the mice result, I'm just giving a summary table since we don't really have time to talk about the detail. So we did the study for the membrane processed effluent. So we used both like our permit and like a final product, means like it's polished water after our permit. So we did find like there is some abnormal like a blood biochemistry indicator for acute acid. So mainly the low globulin. So globulin is like one type of protein. So they can like represent some like a problem for the kidney and the liver. And the high sodium, not really a huge problem, means the dehydration. That means the mice may doesn't like the water that much. And for the chronic study, in addition to like low globin, and we also found some like low platelet concentration in the from the hematology study. So low platelet, like that means there is potential problem with like bone marrow, and it may cause the problem for the blood clotting. And but for the final products after polishing step, so there is like no change compared with the control water. Oh, so as like so many people mentioned, it's not really feasible to do all those like 400 compound like target analysis, non-target analysis, or the whole effluent toxicity or the animal test for all the water. So that's why we are working on some like surrogate list. So this is not finalized list, but this is a kind of like some recommended indicator like we have so far. So for the tier 2 list, like for all the like parameters, actually we can do the real-time test. So even for the TOC, there is like the real-time TOC machine. can be purchased, and for the tier 2, so mainly like we can do the weekly assay, or like if we have some operation condition change, so we can consider those assays. So tier 3 assays is also can be performed under the change of operation condition. So those like whole effluent toxicity assays can really catch up any like non-detected compound, so in the like treated produced water. So we're still working on that. So we will give update once we have the finalized list. Here is the summary of the presentation. So we already like developed like very advanced state of science like produced water quality and analysis method. So we developed those NPDES like plus list to characterize the treated produced water. So I mean those like lists including chemical, physical, biological like parameters. We already use those lists to test the treated produced water from both San Juan Basin and the Permian Basin. We use the like list to evaluate the treatment efficiency of like both thermal-based method and membrane-based method. So the like developed non-target analysis methods can help us to address the concern of the unknowns in the treated produced water. So I mean, so far all the toxicity results like demonstrate so the produced water after appropriate treatment can be like reused safely or has potential to be used safely. And also we're using the analytical result and to do the risk assessment. For example, like we have the like researchers are using the EPA EFAS to assess what is the risk. So by using those treated produced water, we're also like doing the study about the like fate transport of those contaminants so in the soil and see whether it's safe to use for the agriculture irrigation. All right, so this is a teamwork. So I mean, like as the Dr. Shi mentioned, so we have the NPDES like plus committee work on the list like for 3 years. We meet like twice per month, and we have many people are contributing to the work. So like we want to thank the opportunity provided by the like Produced Water Research Consortia, and the students are doing all the field lab work. We have many researchers like giving us the feedback ideas. So we have the faculty from like with a variety of background. For example, the like faculty from biological science, faculty from animal science, and so like we are doing the things together to make sure we can like present enough data to support the like rulemaking process. So we want some the financial support from the state, from the federal agency. So we want like thank all the collaborator providing the like samples, like feedback for our work. So those are the like email address for the presenter today, and feel free to email us if you have any questions. So here is the like New Mexico Produced Water Research Consortium leadership team. So feel free to reach us if you have any questions. So I think that's it for the presentation. So right now we are happy to answer any question you have. Thank you.
Very nice. Thanks so much, Yanyan. Dan and Ryan, thank you so much. Alrighty. Don't be shy in the audience. What questions do you have? None? No way. Alrighty. Well, if there's no questions, we can close out. I know we're a little bit over the hour, but okay. Well, thank you so much, everyone. Um,
Zach, I have a question.
yeah. What's going on, Tim?
Yes, sir. Are these slides, are these going to be available to us, or is it just going to be the video?
You know, that question was brought up earlier in the chat. I'm going to work with Pei and the speakers here to make sure that the slides can be available. So I'm leaning towards yes, but let me confirm with everyone. At the very least, like you had said, the presentation will be available.
Zach, we have one more question in the chat. Are there publicly available data sets related to this work?
I think the publications that everybody referenced in their talks, right? And most of those are available, Yanyan or Zach, through the, correct me if I'm wrong, but through the consortium website, right?
Uh, yeah. So I believe we have the previous presentations like in the consortium website. So definitely we can share the published paper. So if you are interested in the specific data set for the published paper, we can work with you. So for those the things we are still working on, we are still going through the QA/QC process. We would wait a little bit until we get paper published and then we share it with everyone.
John, you have a question?
Zach, this is Mike Hightower. I do have a question.
Oh,
Especially since I have Ryan on. As I think as people know, the US EPA has identified, the New Mexico Produced Water Consortium to try and support their water reuse action plan in produced water. And so some of the recent interactions I've had with the US EPA is of the constituents that we're looking at, the NPDES plus, is there a subset of that we should be using to provide guidance on companies that are testing and researching technologies to try to make sure that they're the areas where we think they need to focus, on, for example, some of the organics, some of the things like the methanols, the alcohols that are difficult that we see as problems. And I've been asked that by industry to have a list that they ought to be looking at. And so I'm wondering, Ryan, with your experience on both developing the NPDES Plus list with the consortium, as well as running activities where you're treating the water, is there a list of things that we should be, concentrating on? And so I'm throwing that out because I'd like to get with the industry folks, like those that have been doing treatment and understand the NPDES Plus list and what the toxicology issues are, so that we can kind of come up with a primary list to be looking at as we do our treatment studies. So I'll kind of hand that over to Ryan to see if he has an idea, and maybe we can get with industry to help us, work that through and provide that to the EPA as we move forward. Because
Okay, I don't want to overkick my coverage there, Mike. I will say that I think some of the other presenters mentioned, the amount of ticks that we were seeing through the various different types of analyzers that we were using was relatively small. I think Pace said something like 75 ticks, and I think ours were maybe like 40. It's going to vary from water to water, and so what that tells me is, the big boogeyman in the room here is the unknown organics. What that tells me is that there isn't a infinite list of unknown organics in this water. It's pretty small, and quite frankly, I think when I look at even our raw produced water, for the 300 and some analytes that we did, the Danforth list, 80% of our raw produced water, 80% was non-detect. So I think that folks are advocating for surrogate parameters. So what we did find with respect to the organics was there's a lot of diesel range organics. There's a lot of aromatics. Shouldn't be a surprise, right? It's an oil-bearing formation. You're going to have a lot of those things, particularly the aromatics. a bunch of different permutations of ringed compounds, lots of those. But I think what we were focusing on were surrogate compounds, like BTEX isn't the be all end all. But if they're non-detect, they're going to behave in similar ways to a lot of the multiple ring compounds I referenced that are going to be in here. So if we know that, there is xylene in this water, if we know that it's non-detect, that's going to behave in a similar fashion to a lot of the other organics that are in there. They can be used as a surrogate to give us confidence that those other things are being removed. And like I said, with the TDS analogy, how tier one, we're doing TDS, and if nothing changes, then I have a pretty good estimate that the majority of that TDS in my treated water is going to be sodium, chlorine, chloride, and calcium. You know, that's what's going to be there. Likewise, what we're seeing is the TOC in our treated water was less than 1 part per million. So that means that any of the organics in total are going to be less than 1 part per million. Now, I think others would argue that some of those organics might have very high toxicity at very low levels. So that's why we do both. But, real-time TOC analyzer, as long as everything is at 1 ppm, that tells me that it's impossible that, dioxin wouldn't be in there at 2 ppm, right? Because then my TOC number would be much higher. So I think that at the end of the day, we're going to be looking at some surrogate compounds. And then I know I think what we're talking with um, TCEQ, if we have so many quarters of non-detects, then we can maybe allow some of those analytes to fall off. But that's why we do this broad net in the beginning. The non-detects are really helpful for us in the industry because we don't want to get 5 years down the road and find out that there was something that might be toxic in here that we never analyzed for. And boy, we wish we could go back and do that. So, one of the people in the chat asked why we're looking for pesticides. That non-detect is really going to be beneficial for us, 5, 10, 20 years down the road.
So I have a list that I've put together. I'm going to run it by you, Ryan, and let you.
Please note that I have no authority. So
I know you have
run
no.
it, run it. Go ahead.
It's as an industry representative that has been doing this for number of years, both in Wyoming, in Colorado, and in New Mexico. So I'll send it to you. Maybe you can give me some input on that. Okay.
Okay.
All right. Thanks, Mike. John, you've been waiting patiently with your hand up. Do you have a question?
Yeah, hey, thank you for this presentation, everybody. Very useful. In the presentation, you had, I think, 6 pages worth of listing out the NPDES plus analytical list by, family types, method types. And then you had a slide on analyzed versus detected, which contains a ton of information in one slide. I'm wondering, is it possible to take the analyzed versus detected and kind of split it apart to those various chemicals listed in the preceding 6 pages, because the 6 pages included things like malathion and whatnot that I'm curious, has that analyte ever been detected in the growing list of analytical library that you have?
Ryan, could you answer the question?
Sure. So John, I know that um, when we did our study of Striker 1 and the Pecos, we were seeing things like, I don't know if malathion was one of the things that we were seeing in the surface in the Pecos, but there were things like that. I want to say that there was a banned organochlorine pesticide that showed up. I think that we did see a hit for 2378 TCDD in the Pecos. There certainly was a lot of PFAS, not a lot. I mean, I want to say maybe about 20. Um, ppt of PFOS in the Pecos, and we did see at the time about 5 in our produced water. Since then, in other pilots, we didn't see any in the produced water. I say all that as preamble to at the time there was a lot more, 2019, 2020, there was a lot more fresh water being added to your fracs than there is now. And I went out on a limb and said, to the extent that we were seeing PFOS in produced water, it was from the fresh water that was being added. So that's one of the reasons why we got to look for all of these things, because you never know what's going to show up in the fresh water. And at trace amounts, if for whatever reason, I think our situation is going to be different. Everybody's situation is going to be different. So for us, we have highly commingled waters, that's all piped. So, we gave some work product to TCEQ showing that 90% of our water at any given time is produced water and maybe 10% is flowback water. Now, somebody else that might be doing treatment on a smaller facility that receives trucked water might receive trucked water from a flowback, where 100% of that water going through is flowback. Their results are going to be looking completely different than ours. So that's one of the reasons why you got to look for all of this stuff. I don't know if that addressed your question, but I do want to circle back and say again, of the list of targeted analytes, even in the raw water, 80% of what we had was non-detect. That's really important in a rulemaking aspect because the regulators they have to be able to defend this to the public, and without one of these reports is 300 and some pages long, and we've done dozens of these reports. They need the body of evidence with the non-detects to be able to say, hey, we're confident with what we're saying. We're confident with the path forward. We've done our due diligence, and these whole classes of chemicals are not going to be in this water.
Ron, I'd like to jump in real quick, and I recognize you threw in there raw water. You do have to be careful. I'm sure you really are about the detection limits that you're being able to achieve with waters that have that matrix interferences. So non-detect means one thing. It means a lot more when you have that number. What was that detection level at the matrix, the water matrix, right?
So that's a very good point, and the standard that we've held ourselves to, and I would recommend as a best practice for everybody else. There's a couple of things there, and that works into the water quality and quantity. When we try to establish a single electronic data deliverable format that everybody uses, and it's good that the New Mexico consortium is working with the Texas consortium. We want to unify that across both states, and the guidance that I've used is that's why we selected the SW846 methods as opposed to the 600 series methods. They can do certain cleanup procedures that aren't really associated with the 600 series methods. And working with Eurofins, where if we do the infrastructure to build a specific project, then that project can be copied to, Exxon and Chevron and Oxy and Aris and TPLT. We can all be using the same project infrastructure. And what we told the lab is, look, we know that you're going to have to dilute to get your sodium on your metals run within the linear range of calibration. So that result is going to be maybe at 100x dilution. But then they're also going to report the minors and the traces through a 1x dilution. So we're going to be getting both. The detection limits are listed on the EDD. And probably the most important thing is we've told the laboratory to report down to the MDL, the method detection limit, not just the RL. So the difference there is the reporting limit is the lowest linear calibration point But oftentimes they can see down another order of magnitude lower than that. And they can give you a non-detect all the way down to the method detection limit. So to me, that's really important. And I agree with you. I've seen past work where folks have said, yeah, everything's non-detect, but the detection limits are, way up here. That's I I think that those folks were trying to game things. With this, we have to be completely transparent. So, I want multiple different dilutions, the stuff that's over the linear range of calibration, report that dilution, and then do the straight run for the other things that are not over that range, so we can get that non-detect all the way down to the MDL.
Did that answer your question? It was a really great response, Ryan.
Yeah, great commentary. Thank you both.
There is a little chat Q&A going on right now, so I just wanted to read that out loud to bring folks up to speed. Um, and Tame was asking, are there limitations to using the human cell lines as proxies, and why would we be using those cell lines as opposed to trophic level organisms? And so Yanyan's been doing a great job answering. Um, Yanyan, did you want to summarize?
Uh, yeah, I mean the current wet assay is mainly for the aquatic organism, so that's why we want use human cell line to evaluate the potential human risk. Yeah, although the human cell lines in vitro assay cannot really representing the complex a biological system, so but it can at least give us some confidence about that, and also we are using the a mice model to verify the toxicity in the kind of high level animals. So I think there is another a question about have you received the feedback from MAD EPA on what we are missing in the term of testing? So I mean I don't know who can answer this question, Zach, Ryan, Dan.
What we're missing? I mean, I'm pretty biased. I think that this is the most comprehensive evaluation of an industrial waste stream. We're looking at this. I think that we're doing a good job, and not to speak for Dan, but I would think that, Dan, I would assume that you would say that, look, there's the volume of water that we're going to be discharging is completely different than any other industrial waste stream. So we have to surpass a higher bar. Having said that, I mean, this isn't a commercial for urethans. The only reason we use them is because there really isn't another laboratory network in the country that can do this much. So, we're kind of bumping up, and even then, we're still doing non-targeted analysis at the university level that even they can't do. So, as far as, your constituents, they're either going to be inorganic or they're going to be organic. And we're getting visibility on just about every classification, uh, you know, every component there, and then the analytes that would make them up. When you start bringing in the mass spectra, there's not a lot of things that we're missing. If it's there, we're going to see it through one of these methods.
Yeah, I'll chime in there, Ryan. I agree that we're looking at this, a lot of this waste stream, a lot of detail, but that's needed as you've talked about and other folks have talked about. So what are we missing? I think the broad brush is it still requires a lot of data in order to start flattening out things that may be outliers or things that you just didn't quite see. Particularly when we come to these pilot testing, there's a lot of progress being made on pilot testing. But if you look at some of the protocols that have been established for quite some time, you finally get down to the nuts and bolts. A pilot test needs to go for a set period of time with no downtime and all the work being done in the field, treatment wise, nothing's being kind of taken back to the lab for polishing, that kind of thing. Recognize that as these pilots have proceeded along within the New Mexico Consortium, it's been doing it longer and is getting geared up in the Texas, we're getting there. Um, so I'm biased. On the other side is that I can certainly say that we're getting there. I still think we've got to get, we can't cut it too short too quick. Just because there, yeah, this will be looked at and should be with a lot of scrutiny. So, fantastic foundational work, and work is continuing with both the researchers and industry in New Mexico State, as well as Ryan and the folks that are doing some pilots. Just keep plugging along and keep that data rolling in for a while.
Yeah, and I think I'll try to tack some other thoughts on here, Dan and Ryan. We're getting quite very similar questions in the chat here of, the wet tests and the human cell lines build confidence, but they're controlled systems, and doesn't there need to be more testing? And I think I'll just, recap Yanyan's most recent paper of, the human cell line testing and then the other tests with wet tests that Mauricio had done of, when you take treated and then polished water and you expose human cell lines and a bunch of organisms to this water, you don't see any sort of genetic or biological signaling that's different than the control samples. Um, I think there's going to be some really good papers coming out on the irrigation of the treated and polished produced water on different crops that's going to show pretty much no response or no bioaccumulation of anything. And so I guess I'll turn the question back on folks is like, when is enough enough? And at what point do you just start stepping through the process of building these facilities? I think the Water Alliance petition on the New Mexico side, and it sounds like from what I've heard, and I'm not 100% sure, but TCQ's approach is to start kind of gradually having these systems go from pilot scale to demonstration scale, right? And then you have a ton of monitoring this NPDES plus list. The amount of sampling and analysis is quite robust from my perspective. And so if you start building into it slowly and you start allowing these things and you're not seeing any differences in, aquatic or human cell line or plants or, any sort of response, I mean, doesn't that seem to signify that the water is quote unquote safe?
Zach, if I could add on to that, because we're expecting to get our TIPDES draft permit here at the end of the month. So we'll get some eyes on that. But one of the things that they said is, yes, you're going to do it in phases. And in order to unlock the next phase, you need to have successful performance at your initial phase for a certain period of time. And, it's going to be looking at all of these things. So I would say the human cell line testing and the wet testing, I think what we're really using that for is to see two things. Is there something in this water that we, for whatever reason, we weren't able to see through one of our analytical methods? Is it, I would, my bias is probably not, it's not there, but these are kind of catch-alls because if there is something there and it is toxic, we're going to see that signal in the wet testing or the human cell line testing. And more importantly, the synergistic effect. So there might be no single one that is a problem on its own, might be below whatever our regulatory threshold is on our permit, but synergistically, are they having a negative effect on the environment? So, I think that's why we need to do these. Again, it's about due diligence. And if we're seeing that, then maybe we go back to the drawing board and say, hey, we're missing something here. If we're not seeing that, then it gives us confidence to move forward. Zach mentioned that there's some plant studies. Ours is one of them. We worked with Colorado State, Dr. Thomas Borch. It's in review now. It's going to be published later this year. But his kind of talking point is, look, plants, they don't have livers. So if there's something toxic, they can't really process it. It's going to be accumulated. You're going to see it. So they're good indicators of toxicity. And then the other thing I want to say here is keep in mind, and it's not an excuse, but we do have to keep in mind the waters of the region that we're discharging it into. We're pursuing something in Texas, so Red Bluff Reservoir. That TDS was 14,000. We're expecting our permit to be probably on the order of 3,000 TDS. I don't know. Well, as soon as I see it, I'll let y'all know. But our technology is going to be able to do way under that. These waters are highly impaired, and really, I think the opportunity that we have before us is really reclamation. I mean, we can make this watershed better because it's so impaired.
Yeah, that is great points. Just to circle real quick back to Zach to what you mentioned. What I heard you say is like, are we there yet? Followed by, however regulatory programs may move forward, it's going to be phased up slowly, which indicates is that kind of what I say, we're not there yet. We're getting there, and we get there by slowly taking steps forward. And as you know, that's I think we're all agreeing on that, right? So I think we do have to say that we're not there yet by saying done, permits, and everybody go do something else. But no one here is saying that. We're saying that, okay, we got to take these steps forward because it's imperative that we get it right. Um, and that's the process. So it's a process still, but it is ramping up.
Yeah, it's a good, interesting differentiation, Dan. So thanks for clarifying that. Um, all right. Any other last questions? I'm going to take silence as a no. So, and with that, we end the webinar.